And the final talk for this session will be given by András Halbritter from Budapest University. And this is joint work of multiple groups with the HAN-REN BME Condensed Matter Research Group at Budapest and ETH Zurich. And the title of the talk will be Benchmarking Stochasticity Behind Reproducibility Denoising Strategies in Ta2O5 memristors. So we're looking forward to your talk. Thanks for coming.
Thank you very much. Okay, so here we have the slides. So it's a great pleasure to be here at this very nice conference. And let me start by acknowledging my colleagues and my collaborators on this specific topic. And that, as it was introduced, I will speak about stochasticity and reproducibility and denoising. So what do I mean by that? So here you see a typical resistive switching characteristic of a memristor, which was measured somehow. And we wish that if we repeat this measurement, then it should be something similar. So this is not good. This is good, but it is not enough to repeat the measurement similarly twice or 3 times, but millions of times. So we should have a very good cycle-to-cycle reproducibility. And also, if we have different devices on the same chip, then they should behave similarly. We should have a device-to-device reproducibility. And also, we wish that if we do not reach the switching threshold, then the conductance state of the device should be preserved for a long time. Okay? So this is something very obvious about reproducibility. But what about stochasticity? What about noise? So here you see another resistive switching curve, which is very similar but much more noisy. And this is actually a problem, because with these memristors, we usually want to implement multi-level conductance weights. And the number of the resolvable conductance weights is nothing else but the smallest resolvable conductance delta G over the width of the conductance window that we use. And this delta G depends on many things, but it's quite obvious that this delta G cannot be smaller than the conductance variation introduced by the noise. So what do we know about the noise? For instance, is the noise in such a switching cycle reproducible from cycle to cycle? Do the noise amplitudes show similar characteristics from device to device? Is the noise preserved if we keep the voltage below the switching threshold? And does the noise have some kind of voltage dependence? I will try to answer these questions along this talk. So first of all, some brief introduction to noise measurement. So let's assume that we have a piece of a conductor, we have a fluctuator with a certain time constant, then we will have some resistance fluctuations. We can calculate the spectrum, and this will be a typical Lorentzian spectrum, which is constant until 1 over the characteristic fluctuation time and decays with 1 over f squared afterwards. But if we have many fluctuators, then the Lorentzian spectra of the different fluctuators are superimposed, and then finally we will have a much shallower spectrum, which is a kind of a 1 over f type noise. And in a memristor, we can have very special situation where we have a 1 over f type noise and we have a bump superimposed. And the 1 over f type noise is actually the signal of many more remote fluctuators, but we have a fluctuator that is placed just at the device bottleneck, and this is a dominant fluctuator with this Lorentzian contribution. How do we measure the noise? And first I would speak about the steady state noise measurement, where the idea is that we have steady state fluctuations. So even without any driving, we have fluctuations in the sample, and we want to read out these fluctuations. And thereby, we need to use a rather low voltage, and we have to stay in the linear part of the IV curve to measure the noise of these steady state fluctuations. And we can indeed measure the noise spectra. Then we can integrate the noise spectra for a certain frequency band. Thereby, we get the mean square deviation of the conductance. And you see that this mean square deviation of the conductance scales with V squared, which is a kind of an obvious scaling, because if we have steady state conductance fluctuation, then just by Ohm's law, the current fluctuation will scale with the V squared. And then if we rearrange this equation, then we get that the relative conductance fluctuation, so the variance of the conductance over the conductance, is the same as the relative current fluctuation over the current. And this is something which is a good measure because it doesn't depend on the driving voltage, but we should stay in the steady state if we want to have this equation satisfied. Okay. And then we can measure this relative conductance fluctuation as a function of the conductance for many different devices, many memristive systems. This is a kind of a noise map. And on this noise map, we can see interesting tendencies that in some regions, the relative noise is a power law function of the conductance. But I wouldn't go to the details of all of these colors, but I would concentrate on a specific material system, which is tantalum oxide crosspoint devices, where we measured 8 samples, 150 junctions, and here we see the noise map for that. And here we can also see some tendencies that in the high conductance region, the relative fluctuation is scales with minus third power of the conductance. In the low conductance region, it is mostly constant. And this can be actually explained by simple models. In this region, we have a single fluctuator in a diffusive junction. And in this region, we have a broken junction, a barrier-like transport. I wouldn't go to the details of that. We do not have enough time for that. But I would focus your attention on an additional issue, that the transition between these two regions occurs around the conductance quantum unit, which means that in this region we really have truly atomic sized filaments. But during this talk, I would rather concentrate on the amplitude of this fluctuation. So we have this noise, or this noise map for many memristors. And the question is it good or not? Is it a high noise or is it a low noise? And for that, I would quote this very nice paper from Joshua Young's group, where they have achieved 11-bit resolution, so 2,000 different conductance states. For that, they used the denoising procedure, and actually I would go more deep to understand similar denoising procedure in our devices. And they have achieved a conductance resolution which was 2 microsiemens, or in other words, 0.026 conductance quantum unit. So I would use this conductance resolution as a reference, and we can plot this conductance resolution on this noise map. This noise map is delta G over G, so if we have this reference resolution, then we have to divide it with the conductance, and this is this black line. And it seems okay because all of the data are below that, or most of the data. But actually here, this is the variance of the conductance. But if we want to have this conductance resolution, then the peak-to-peak variation of the conductance should be smaller than the reference resolution. And thereby, we should put the border a bit below. So let's say we can put it 3 bits below, so at a level which is 8 times smaller than this conductance resolution. Okay? So the noise data below this dashed line have good enough noise to have this conductance resolution. And the data above that do not have enough noise, do have larger noise, and this is the data for the tantalum pentoxide samples. And what is very interesting, that there is very large device-to-device variation of the noise. For instance, we can have points which are well below this reference resolution. We can have a point at the same conductance which is well above this reference resolution. And the question is whether we should throw away these devices because they do not have low enough noise, or whether it is possible to decrease the noise by some procedure. Okay? And for that, it is very useful to go beyond the steady-state noise measurements. So not just to measure here, but to track the evolution of the noise all along the entire IV curve. But there is actually a problem, because the IV curve depends on the speed of the measurement. And let's say that I measure an IV curve with 10 Hz, and then I make a much slower noise measurement, and then the noise measurement has nothing to do with the IV curve. So if we want to match the data, then it is very important to extract the noise data and the IV data from exactly the same measurement. And that's why we have a special measurement technique where we can ramp the voltage in a step-like fashion, extract the noise data along the steps, and then we can have both the IV data and the noise data from the same measurement. Here you can see an example. This is a resistive switching IV curve for 10 cycles, so they are very reproducible. And this is the noise measurement. The gray lines are the noise measurement for the 10 cycles, which are not really very reproducible. Okay? And here we can make the trick that we measure the noise at low bias, so in the steady state, then we make a cycle, then we measure the noise again, then we make a cycle again, and repeat it 10 times. And here you can see the variation of the noise data for these cycles, which means that the cycle-to-cycle variation is actually the same as the device-to-device variation. It seems to be a bad news for the first side, but actually it is not, because this means that if I have a device with very high noise, then I can just make some cycles and measure back the noise, and if the noise is low enough, then I can stay there and continue the measurement. But actually, it doesn't seem to be a very good idea that I want to denoise a certain state, and for that, I first switch to another state to make a cycle. So it would be even better to make this denoising without making a switching. And here, I would focus your attention to this figure, which is the average, so the color is the average noise along the whole switching cycle. And here you can see that at low enough voltage, the noise is constant, which is quite good for a steady-state noise measurement. And here you can see that the IV curve is super linear. Here we have the switching threshold. But already at around half of the switching threshold, the noise starts to go up, and there is an order of magnitude increase in the noise, which means that with the voltage, we are already exciting further fluctuations in the sample. And this could be used to mobilize the fluctuators and to manipulate them. Okay? So the next measurement scheme that we use is a so-called sub-threshold cycling, that we make a noise measurement at low voltage, then we ramp up the voltage to a certain voltage, but this is below the switching threshold. Then we go down, and then we measure the noise again, and we do it 10 times. And first, we only do that in this region, where the average noise is constant. And indeed, for the 10 cycles, the noise values are quite reproducible, which is good news, because at low enough voltage, we can preserve the noise. But if we go a bit higher, so we are still below the switching threshold, but we go to this region, which is a kind of a precursor noise region, where the increase of the noise already signals that we are approaching the switching. In this case, we can avoid the switching, but if we make these sub-threshold cycles, then we can see that again, the noise after the 10 different cycles, sub-threshold cycles, spans the device-to-device variation. So just by this sub-threshold cycling, we can do this trick that originally we have a higher noise, then we make a sub-threshold cycling, and then within 10 cycles, we have a good chance that we will find a state where we have low enough noise that we are below the reference resolution. Okay? And then I would conclude this part with a few remarks that we can use this precursor noise in this region below the switching threshold for single conductance state denoising. And afterwards, if we stay in a certain state, but we also stay at low enough voltage in this region, then we can preserve the noise of the state. So if we look at all of these data, then we see that it is bad news that we have a huge device-to-device variation of the noise. It's more than an order of magnitude. But as a good news, we can denoise the conductance state just by this sub-threshold cycling. it is also good news that the noise is stable if we keep the voltage in this region. It is a bad news that this is a kind of a trial and error approach, that we make it several times and then we read back the noise, but usually within 10 cycles we can get to a quite low noise level. And as a final remark, this trial and error approach is not really a problem if at the end of the day we want to use these states for static weights in a neural network, because then we once make the denoising after programming the conductance state, and afterwards we can use this state for further operation. Okay, and here I have a final figure where I summarize some further merits of noise analysis, but I won't go to the details, I just have some references here. And there is also a very interesting issue, because here I spoke about the urge to decrease the noise, but there are some cases, which was very nicely demonstrated by the group of John Paul Strachan, that in probabilistic optimization, noise can be quite useful. And actually we studied this problem and placed the optimal noise for solving a Max-Cut problem with a Hopfield neural network on this noise map. And the optimal noise level is actually here, which is 15 or 13% of relative noise, which is an extremely high noise level on this entire noise map. So usually the noise is smaller and we have to add additional noise, which is easier than denoising the system. So thank you very much for your attention.
So thank you very much. Are there any questions from the audience? So maybe let me start with one. When you showed your cycle curves, the cycle curve under noise had a significantly different shape. Is this something that you would rate as a challenge of developing the benchmarking procedure, or already an indicator that the noise level of this type of memristor is simply too high?
So it is actually not necessarily high, as you see from this noise map, but it is not very reproducible. Okay, we have a region here where it may change, but if we go back, then it is reproducible, which means that with the voltage we manipulate, for instance, the characteristic time of the fluctuator, but this is reproducible. And then if we go to this range, then it's already not reproducible. So if we go there and go back, then we will have something completely different. And of course, during the switching, it is also not reproducible. So this is true data. This is not measurement error, but this is true data, which you can clearly see if you go to the details.
So the memristor designers will need to improve their designs a bit further.
Yeah, I mean, this denoising is a good strategy for some solutions, but it would be even better to have solutions where somehow the material design grants the reproducibility and the retention of the noise. So this is an open question for the society here.
Well, thank you very much. Are there any further questions? If not, then let's thank the speakers again.
Thank you.